What I want to talk today about is the closure and the interior. We started talking about the closure at the end last time, I believe. I also want to talk about the interior of a set, which is kind of some kind of complementary notion to the closure. Is the interior of a set. But anyway, let's talk about the closure just to refresh our memory. This is what you are familiar with from analysis. The closure uses the bar, and that is something like the closure. Actually, in our book, they use the bar, but they also use this notation, like closure of 1, 2, 3, something like that. This is not very interesting. This is just 1, 2, 3. So the CL means closure. Why is the closure of 1, 2, 3 equal to 1, 2, 3? Remember, the closure means the smallest closed set, which includes that set. And the set 1, 2, 3 is already a closed set in the the standard topology of R. And so when you take the closure of that, it's still just itself. It is a closed set. More interesting example would be something like the closure of Q. This we talked, I think, about last time, is all of R. If Q, remember, is just the rationals. And if you start with just the rationals and you throw in all of, the analysis way of talking about this is you include all the limit points. That actually includes every real number. Everything is a limit point of rationals in the real line. All right. Actually, there's a word for this when, here's a little terminology on the side. I'll write this as a little definition. We're not going to talk a lot about this in this course, but it's a big deal. When A is a subset of X with A bar equals X, so that is, A is a subset where when you take the closure, you get the entire space, and that's like this. Q is a subset of the real numbers, but when you take the closure, you get the entire space. It means basically that set exists everywhere in the space, and all the other points are really close to elements of that particular set. The word for that, then we say A is dense in X. All right, this is one of the favorite fun facts about real analysis is that Q is dense in R. That means that every element of R is sort of arbitrarily close to a rational number. Dense, more generally in topology, means this, when the closure is equal to the entire space. All right. Anyway, can we talk about the definition of closure? Closure is like closure of A is I'll put this in quotes, the smallest closed set containing A. That's the idea. This is how you should think about the closure of a set. That is one of the ways to think about it. But that actually is not the way that we wrote the definition, just because the word smallest is a little ambiguous about what exactly I mean by smallest set. But one way to write the definition, and this is what I wrote, I believe, at the end last time, was that sorry, I'm just trying to write down. This is the closure of A. It's defined to be the intersection of all closed sets containing A. All right, the intersection of all closed sets containing A. That's the definition that we're going to use for the closure of a set. The intersection of all closed sets containing A. All right, I want to talk about some simple facts about the closure. So first theorem, actually this I'm going to leave for you to do on the homework, but I will write it down because it's super important. A equals A closure. Anybody, what does it mean if A is the same as A closure? This means something about A. then it is closed. Yeah, this is what happens if the set is already closed, then it is equal to its own closure. So A equal A closure, this is actually a if and only if A is closed. All right? That is a simple fact about the closure of a set. Okay, like I said, this is going to be on the homework for you to do the proof, so we don't need to elaborate on that. Let's talk a little bit about the closure is the smallest closed set. That's what I said several times. The next theorem is a way of actually saying that, a sort of specific, I'll write it all out. The smallest closed set containing A. All right. This is what I kept on saying before. Here's a theorem that is actually trying to say that specifically. There's really two parts. First of all, the closure is a closed set. And second of all, is this business about smallest. So I'm going to write in two parts here. The first part is first just that A bar is closed, right? So the closure, it really is a closed set. And second of all is the thing about smallest. What do I mean by smallest? I mean smallest in terms of subsets. So that all the closed sets containing A, you can look at them as sort of subsets of one another, and the smallest of those, the one which is a subset of all the others, that's what the closure is. So I'm going to write it this way. If A is a subset of C, and C is closed, then A bar is a subset of C, all right? This is the smallest. It's a little, I don't know if it's obvious reading those words why this means something about smallest, but it says if I have some closed set, then A bar is smaller than that. This is basically what that means. If I look right here, my interpretation of that is A bar is smaller than C, but C is just any closed set containing A. So A bar is smaller than any closed set containing A. And that's what I mean by, this is the technical way of saying that it is the smallest closed set containing A, because it's a subset of any closed set. A bar is a subset of C. All right. Can we try to do the proof of these? Actually, each one of them is just like one sentence. So they're very easy to see why they are true. So the first one, A bar is closed. Number one, A bar is closed. Remember, you have to use the definition of A bar. A bar is the intersection of all closed sets. A bar is an intersection of closed sets. Actually, that automatically makes it closed. This is something we talked about last time, or maybe the time before. It's a theorem that we had about closed sets. Any intersection of closed sets is closed, and any finite union of closed sets is closed. All right, so A bar is an intersection of closed sets. That's part of the definition. So it's closed. End of story for that one, right? It is a closed. It is a closed set because it is an intersection of a bunch of closed sets. It's the intersection of all closed sets which contain A. All right. And what about the second one? If A is a subset of C and C is a closed set, so I'm going to say let A be, what it says up there, with C closed. All right. So that means C is a closed set containing A, right? Those are just other words to say the same thing, right? C is a closed set containing A. And the definition of the closure is defined as all the intersection of all closed sets containing A. So if C is just one of those closed sets, The intersection of all of them better be smaller than that, because when you take the intersection of something, it gets smaller. All right, so C is a closed set containing A. A bar is the intersection of all closed sets containing A. And so that's smaller, right? Containing A. So A bar is a subset of C. C is just one of those closed sets, but A bar is the intersection of all of them. And so that has to be a subset. All right. I said they were one sentence each. I guess that's 2 sentences maybe. But simple enough. All right. These are basic facts about the closure. The closure is the smallest closed set containing A. All right. Anybody got thoughts about this? Okay. I would like to talk about the other thing that I said at the beginning we were going to talk about today. What I want to talk about today is the closure and the interior. This is sort of, I don't know if anybody ever wondered about, can't you do like the same thing but make it open? That's the closure is kind of like you make it closed. You add some stuff into it to make it closed. Can you do a similar thing to make it open, like the openger or something? The answer is yeah, you can do that. It's not called the openger. It's called the interior. So I'm going to say this is like a dual notion, and it's called the interior for reasons which we will see. The interior of a set. And the notation for that is we're going to write int of A, or the sort of, the closure, sometimes we use the bar. The interior is written like that. A with the little sort of IKEA style accent on the top there. All right. That means the interior of A. All right. And what's the definition? It's basically like it's like the closure, but you just sort of do the opposite of all the words. So if I could say, not the opposite, but the complement or something like that. So the closure of A is the smallest closed set containing A. The interior of A is, I'm going to try and just kind of reverse all those words except for is and the. Biggest open set, and rather than containing A, it's which is contained inside of A. This is what the interior is, the biggest open set inside of A. All right. Now, again, that's not typically used as the definition just because we don't like the definition to have this word biggest in it, which is a little ambiguous when it comes to set theory. So rather than use the word biggest, it's done in the same way that the closure was taken as the intersection of a bunch of big closed sets, originally arriving at the smallest possible closed set. The interior is defined as a big union. You union all of the open sets inside of A, eventually arriving at the biggest open set inside of A. So here's the true definition. It says the interior of A is the union of all open sets U, with U being a subset of A. This is the interior, the union of all the open sets inside of A. All right. And what you end up with when you take the union of all those open sets, you end up with the biggest open set, which is inside of A. All right. So, for example, can we just some very simple examples in R with the standard topology? This probably is something that you did not talk about in your analysis class, but it's, you might as well. It's not really any harder than the closure. What is the interior of the closed interval 0 to 1? This is the standard example. Yeah.
Is it 0 to 1 but open?
Yeah, it's the open interval 0 to 1. Remember, the interior is meant to be the biggest open set inside of that. And the biggest open set inside of that would be the open interval from 0 to 1. Yeah, great. Any thoughts about that? So this is kind of, if you think of the closure as like you add in a few more points to make it a closed set, the interior is kind of like you take away a few points to make it an open set. It's the biggest open set, which is inside of what you started with. Taking the interior involves removing some points to make it into an open set. All right. How about this? R, the interior of R. That is, you start with everything and remove a few points, or maybe a lot. I mean, it's not always a few that you have to remove, but to make it open. This may be slightly a trick question. I don't know. Anybody, any thoughts? Yeah?
Is it just R?
It's just R. Yeah, why do you say that?
Because R is open.
Yeah, R is already open. And so you get the same thing when you take the interior. Just like the closure of a closed set is the same set again, the interior of an open set is the same set again. So this is true because R is already open. So if you think about what's like the smallest amount of points I can throw away to make it open? Well, it's already open, so you don't throw away anything. All right. The interior of an open set is just the same as what you started with. How about this? Z, the interior. This is a little weird, although if you think about this in terms of pictures, at least for subsets of R, these are not. Z looks like this, right? Just a bunch of individual points, big old points. The interior means the largest open set inside there, all right? I don't know if you were thinking about it in those terms, but that is how you could have thought of, say, the first example is a closed interval. All of these points, including the endpoints. What's the biggest open interval you can stick in here? Well, I can stick an open interval right in there, right? Which takes up the entire interval all the way up to the ends, but not including the ends because it's open. What about this one? For Z, what's the biggest open set that you can stick inside there? Yeah?
Is it R?
Is it R? She was sort of shaking her head. Well, it can't be R. Like R doesn't fit inside those points. Although you should feel sort of like this is going to be a stupid answer. I think the answer she's thinking of is like you can't put an open set inside of those points. There isn't any, like there aren't any open intervals, which are a subset of Z, right? So what does that mean? Does that mean there is no interior? In such a case, you say this is the empty set. Remember, the empty set is automatically open, right? And so the empty set is always available as like a worst case scenario if there really is no open set in there. Actually, well, there is an open set. I mean, the empty set is an open set, which technically the empty set is a subset of Z. And so it is the empty set. So Z has empty interior. This is like, you could say, kind of the opposite of being dense, or it's the dense means the closure gets you everything. This is a set for which the interior gets you nothing, all right? Although there isn't, as far as I know, there isn't really a word for that. We just say empty interior. It works all right. You don't need a word for that. Okay, how about, I was going to also ask about Q. The interior of Q. Again, you should think of, on a picture here, Q this time looks like, it's sort of like points everywhere, but not in any intervals, right? They're all over the place. I mean, yeah, not in any intervals, right? Again, there are no open intervals that are a subset of Q. And so Q has empty interior, right? Q is actually fairly extreme in this sense because Q has empty interior and it's also dense. So when you take the closure, you get everything. When you take the interior, you get nothing. So Q is both of those things. It is dense with empty interior. It is possible. All right. This is the interior of a set. Any thoughts about that? It's not all that confusing. I mean, it's kind of like the closure, only backwards or something. It's a dual notion to the closure, I would say. All right. And can I just say, we get very similar theorems about the interior. Because the definitions are so similar, just using opposite words every time, you can prove the same theorems. So it's kind of like every theorem about the closure has a corresponding theorem about the interior. And so I'll write, here is a theorem about the interior, just like the closure, the sort of smallest set closure theorem. This one, I'm going to say, first of all, A interior is open. When you take the interior, you always end up with an open set. And then secondly, this is the thing about, it is the biggest open set. So this says if U is a subset of A and U is open, then U is a subset of the interior, right? That means that the interior is the biggest open set, which is inside of A. Because if you have any other open set inside of A, it is automatically a subset of the interior. It's smaller than the interior, all right? And the proofs of these two things are exactly the same as the closure proofs that we just did, only you say, every time I said closed, you say open, and every time I said intersection, you say union. So the first one, why is the interior open? It's because the interior, I'm not going to write this down, but it's the same stuff. It's because the interior is the union of a bunch of open sets. That's the definition. And the union of any open sets is open, so the interior is open. And the second one, if the union, or if some open set is a subset of A, remember A, the interior is defined to be the union of all possible open sets inside of A. And so if you have an individual one of those open sets, it is automatically a subset of the union of all possible open sets. That's why this second one is true. Same stuff from before, all right? And we get the same fact. Remember the other theorem I wrote about the closure, which I said was going to be on the homework? I thought let's just actually do this one for the interior. About, this says A equals A interior if and only if A is open. All right, let's try that. This is also not so hard. So the proof, this is a if and only if, so you have to do two directions here. This one is easier, so let's try this one first. You assume A is open? What? Sorry, I meant the other direction. I wrote the arrows backwards on my notes. It doesn't matter what order you do them in, but this way is easier. So we assume that A is equal to A interior. And then I want to show A is open. This is like, if you see it, this is very, very easy to connect the dots here. Can anybody say why this is true? Yeah?
Because A open is the union of all open sets in A, so if they're equal.
Okay. Yeah, this is correct, although more complicated than you need to say. In this case, actually, you can. Anybody see how to? You can make this argument like without saying much of anything. In this case, yeah.
Is it just A interior is open, so then if they're equal, A has to be open?
Yeah. What I want to show is that A is open, but I'm assuming A equals A interior, right? So really, then what I need to show is that A interior is open, but it is open. Like that's this, right? A interior is open. What Alvin said was basically the proof of this again, which is fine, but not necessary here. So I want to show that A is open. I can just say A equals A interior, and A interior is open. So A is open. Right. So that was the easy one. Thank you for your contributions for the easy part. The other part is not much harder, but you have to say a little bit more. So this time around, I say, assume A is open. And then I have to show A equals A interior. All right. To show that set equality, we're going to show two subsets. All right. So to show that A equals A interior, we'll show that A is a subset of A interior and A interior is a subset of A. All right. And this one here is, we already know that just because of the definition. A interior is the union of all open subsets of A. And since it's a union of everything, all those things are subsets of A, then the union of all those things is a subset of A. So this one is, since A interior is a union of subsets of A. All right. And what about the other one? We have to show A is a subset of A interior, and this one is where we use the assumption that A is open. A is open. So that means actually that it must be part of the interior, because the interior is the union of all open sets, or you could say the interior is the biggest open set which is inside of A, right, by this this number 2 here. So A is open, so A is a subset of A interior by, the number 2 that we just did. Because the interior is the biggest of all the open sets. So if you have another open set, it has to be a subset of the interior. That's what that is all about. All right, I would like to do some examples where we can actually draw some pictures of things for the rest of the time. I think we've done enough proofs for one day. I don't know if you feel that way. I'm just getting started, but I will do the rest of my proofs today in private. All right, let's talk about some examples of interiors and closures. We did a few simple examples in R. Let's talk about, just to get a little fancy about it, let's try some example in R with the lower limit. Our book writes that as R sub L here. This is, remember, this means the lower limit topology. That's the one in which open intervals look like this. All right, that's the lower limit topology. When you use the lower limit topology, everything looks different, or at least some things look different. I don't know. So in the lower limit topology, let's talk about the interval from 0 to 1 like that. Let's call that A. And I want to know, what's the interior of that? What's the closure of that? Let's discuss. One of those is easy to answer. The other requires some thought. What about the interior of that? Anybody feel like you know what the interior is? Yeah?
0, 1, like non-inclusive.
This is an interesting idea. If this were the standard topology, you would say the interior is the open interval 0 to 1, not including both the endpoints. Actually, I think it's different with the lower limit. You have
The empty no.
could be the empty set. It's not the empty set, actually. Yeah?
Is it just A itself?
I think it is A itself. Why do you say that?
Because we defined it as open. So
Yeah. This, in the lower limit topology, a set like this is open, right? And so its interior is equal to itself, because the interior of an open set equals the whole set. So I'm going to say this is open, so A, the interior, is the same set again. All right? Slightly weird, I guess. Okay, what about the closure? This is actually a little stranger. I don't know. They're both strange. How about a closure? A bar. In a bar, you might think I'm going to have to add some points in to make it closed. Although, if you ask me, I have a hard time thinking about what even closed looks like in this universe, right? Open looks like an interval which is closed on the bottom and open on the top. What does a closed set look like? I thought maybe for fun we should think about, for example, can I look at the complement of A? Remember, closed means the complement is open. So if I'm starting with A, let's look at R minus A just to get a feel for. This will be closed, right? I'm trying to get a feel for what in general will a closed set look like in the R with the lower limit topology. What is R minus A in this case? You know, if A looks like the interval 0 to 1, including 0 but not including 1. What's the complement of that? It's everything outside of that. So it sort of is in two pieces in this example. There's the piece on the left is, I don't know why I wrote the word is. Can I just use the equal sign? There's this part over here. And then I'm gonna say union with this part over here. And the piece on the left looks like minus infinity to 0, not including 0. That's this part, the left side. And then union, the stuff on the right, the complement would be yes, including that point. So this is like 1 to infinity, like that. All right? That's like this part and this part in the complement. And you just have to think carefully about, does it include this point or not, the various endpoints. All right? And then what about those two parts? Well, actually, this one is open, right? In the lower limit topology. Because it is an interval including the lower endpoint, but not the upper endpoint. This one actually goes out to infinity, but that's still allowed in the lower limit topology. And what about the other set? Actually, the other set is also open in the lower limit topology because it is an interval which doesn't include its right-hand endpoint. Now, this one also doesn't have a left-hand endpoint, but actually that you can make this as a union of intervals that do include the left endpoint, where you just make the left endpoint go down to minus infinity and take the union of all those. So actually, both of these are open. All right. So what's my conclusion then? R minus A is open, right? So that means A is closed because its complement is open. All right? Is this confusing? In the first part, we said A is open, right? And it is. We now have realized actually also A is closed. So in the lower, so that means, well, as far as the closure goes, A bar equals A, right? Which is this set 0 to 1. All right. So actually in RL, the lower limit topology, a set like this, interval A to B, is clopen. It is open and also closed. Every one of those intervals is open and also closed. This is very weird compared to the standard topology for R, in which the only clopen sets are empty set and the entire, all of R. But in the lower limit topology, many sets are open and closed. All right. Very strange. So in this case, the closure and the interior are not very interesting because the set is already open and closed, so you don't get anything else when you take the closure or the interior. All right. What about the finite complement topology? Can we talk about that? How about R, the finite complement? Do we write? I think they write like that, right? In our book, RFC, the finite complement topology. All right. Again, let's look at this set. This is a more interesting example because this is not open in the finite complement. It's also not closed. So it's this up to here, not including the right side. All right, what is the interior and what is the closure? So we need to think about, let's talk about interior first of all. This would be the biggest open set inside A, right? Where, of course, open, when I say biggest open set, I don't mean the biggest open interval in the ordinary sense. I mean in the finite complement topology, the biggest open set inside of A. This is A here. All right? You have to think about what does an open set look like in the finite complement topology? Remember, an open set looks like it includes all real numbers except for a finite set. So an open set, open in RFC, looks like a set which includes everything except omitting a few finitely many points, right? Here I've omitted just 4 points, but it includes all other points. So what is the biggest open set inside of here? Or perhaps, I mean, is there any open set inside the interval from 0 to 1? And if so, what's the biggest one you can get that's completely inside here? Any thoughts? I would say, yeah?
Is it empty?
Yeah, I think there is no open set which is inside here because every open set looks like this. It includes all real numbers except for certain individual finitely many numbers. None of those things live inside there, right? Inside here has to be confined to just inside this interval, but every open set in the finite complement stretches across the entire line except for a few points. All right, none of those are a subset of A. So I'm going to say no non-trivial open set is inside A, right? Because in the finite complement topology, every open set has to cover the entire line except for finitely many points. And none of those can be inside the set A in this example. No non-trivially open set is inside A, so that means the interior of A is the empty set. The empty set is an open set. It's the only one which you can fit inside of A. All right. And then what about the closure? So the closure of A, this would be the smallest closed set containing A. All right. We should think about what does a closed set in the finite complement topology look like? An open set looks like this, right? It includes everything except for finitely many things. A closed set, closed in RFC, looks like, well, it would look like the complement of a set like this, right? This is what an open set looks like. It's all real numbers except for a few points. The complement of that would be a closed set. That would be just those extra few points, right? A closed set looks like just like this. It's got nothing in it except for a finite set of points, all right? Really, it looks like a finite set. That's what a closed set in the finite complement topology looks like. And so, what is the smallest closed set containing A? I'll draw the picture of A again. A looks like this point up to here. The smallest closed set containing A? a closed set looks like just finitely many points. I would say no set of finitely many points can contain all of A, right? Because A is infinite. So that means no finite set contains A. So when we take the closure, you can't actually make it into one of these sets that look like this because none of them include A. And so you have to just use all of R. That always counts as an option for a closed set, is all of R. No finite set contains A. So the closure is all of R, right? There are no smaller closed sets that can contain the original set, because another closed set would have to just look like a finite bunch of individual points, and those cannot contain A. All right, so A bar is all of the real numbers. So this is another example, I guess, of a set which is dense and and has empty interior, right? The interior is the empty set, and the closure is the full set of all real numbers. All right. We got a few minutes left. I want to say one more thing, one more way to think about interiors and closures is in terms of how do you tell if some point X is in A interior or A closure. There's actually, if you can look at a picture, there's a fairly simple way to tell. X is in the interior of A. This means that X is, remember, interior means the union of all open subsets. So when I say X is in the union of all the open subsets, it means X is in some open subset of A. Really, this means that X is in U for U. X is in U, where U is an open subset of A. So this, I don't know if that looks complicated the way I wrote it, but actually this is a very simple way to think about what it means to be in the intersections, what it means to be in the interior is what I meant to say. So if I have a set A like this, and I have some point X, how can you tell if X is in the interior or not? It's in the interior means that X is part of an open set where the open set is inside of A. So really what that means is X has a neighborhood, U, where U is inside of A. If you can make that neighborhood, then X is in the interior of A. So this is the picture to have in mind when you think of what X in interior of A means. It just means that X is in some neighborhood inside A. All right, and that's a pretty nice way of thinking about it, I think. And what does it mean to be in the closure? This is a little harder to reason out why this is the case, but I'm just going to tell you. X in the closure. The picture is still easy enough to think about. It means X is part of every closed set containing A, although it's a little hard to think of it in those terms. The picture for the closure means that if you imagine X being sort of on the edge, or it could be fully on the inside. That still counts as part of the closure, right? X in the closure means that any neighborhood of X intersects with A. All right. So in the interior means there's a neighborhood that is totally inside of A. On the closure means that any neighborhood around the point touches A. So like this point is in the closure and also in the interior, but this point here is on the closure. It's not on the interior. But being on the closure means that any neighborhood around that point must touch the set A little bit or a lot. All right. This is a good way to think about points on the interiors and the closures. All right. One more cute example, and then I'll leave it. So I think I haven't said this yet, but I think you've all gathered. For any set, we have, our book uses this cute phrase, which I've never seen before. We have a set sandwich. Getting hungry just talking about it. The interior is a subset of A, and that's a subset of A closure. The book calls this a set sandwich. The original set is like sandwiched in between the interior and the closure. All right. So the interior is a little bit smaller, and the closure is a little bit bigger. That's the basic idea. When I say a little bit, that's usually the case. Sometimes it's much bigger. Sometimes you take the closure and get the entire space. But here's an example. How about let's say in R2, just so that we have a cute example in R2. Let's say that A is sort of this weird kind of balloon sort of a thing. But it has a dotted line there. That means it does not include any of the points on the boundary of the balloon part, except for the one at the end of the string part. All right. Let's say that's A. Can we say what is the interior and what is the closure of A? Well, let's talk about the closure first. This will be a little bit bigger, or sometimes it's a lot bigger, but you want to include all of the, you sort of want to add in the points which were missing before. What do you think?
The dotted points, we can add them in.
Yeah, we should add in the dotted points. And I could say, like, I hope that that's all what you had in mind. Why do you have to add the dotted points in? It's because those points right on the edge, they do have that property that any neighborhood around that point touches the original set. And so those points need to be part of the closure. So the closure of that set is the same, but it includes that sort of circle around the balloon part. That's the closure. All right. I didn't draw the string exactly the same, but did anybody wonder, do you need to like make the string part thicker or something like that? Beef it up a little? The answer is no, you don't. Like if you think about, if I took a point which used to be right next to the string, should I beef out the string in order to include that point? The question, does that point belong to the closure? The question is it true that every neighborhood around that point touches the string? And the answer is no, it doesn't. You can make really small neighborhood near that point that doesn't touch the string. So we should not beef up the string at all to make the closure. All right, and what about the interior? The interior, and this will do us for today, I think. The interior is, what do you think?
This is just a dotted circle without the string.
Without the string, yeah. It's this with the stuff on the inside too, right? But no string. All right. Why did you throw away the string? Because those points on the string are not part of the interior. That's because if you put a neighborhood around one of the points on the string, that neighborhood is not fully contained in A. That's what it means to be in the interior, is this, right? And that's not true of the string points. They are part of the closure, but not the interior. So this one, no string. All right, I think that'll do for closure and interior.